Right, in this mini lecture, we're going to talk a bit about correlation, and in particular Pearson's R, which is the most common measure of correlation, so we'll focus on that. So correlations basically test the relationship between two variables. Bivariate correlation is simply a measure of the direction and strength of the linear relationship between two variables. So that's kind of an important point, is that it tests linear relationships and not curvilinear relationships. So relationships that where the variables are either positively related, whereas if variable x goes up, variable y also goes up, or where they're inversely related, where when variable x goes up, variable y goes down. But it doesn't test more complex relationships where as variable x goes up, y might go up to a certain extent, and then at some point y might go down. So it doesn't test like curvilinear relationships. Typically, but not always, the two variables being tested to see if they're related to each other will be interval or ratio variables, but there are forms of correlation that work with involving ordinal or binary variables. In order to test a correlation, basically, you need scores on each of two variables for every case or every participant in the data set. So we'll call the two variables variable x and variable y for short. So it's important to note, although this isn't really a research methods course, it's important to note that correlation coefficients do not provide any information about cause and effect relationships, or they're not enough information to make claims about cause and effect relationships. So many people often mistake a correlation between two variables as meaning that one variable causes the other, and that just simply is not the case for a number of reasons. It could be variable x causes variable y, it could be variable y causes variable x, it could be both variables are being caused by another variable, or it could just be like a chance relationship between the two variables. So correlations simply are a measure of the degree to which two sets of paired scores vary together in a consistent linear manner. If they don't vary, then your correlation will be quite low or likely close to zero. As I mentioned, the most common correlation statistic is Pearson's R. So sometimes when you hear correlation, it basically means Pearson's R, although there are alternatives to Pearson's R. Pearson's R ranges from -1 to 0 to +1, where +1 would be the strongest possible positive association between the variables. So as if variable x increased, variable y would also increase in a perfect linear direction if the correlation was +1. -1 indicates a perfect inverse relationship, or negative relationship as it's sometimes called, between the variables. In reality, correlations tend not to be that strong. They tend to be, it depends on the field and specifically what's being studied, but in many areas a correlation of 0.6 might be considered rather strong, or a correlation of -0.6 would be considered a rather strong inverse correlation, but it really does depend on the context. But basically, the closer to 1 a correlation gets, the stronger it is. The closer to 0 it gets, the weaker it is. And correlations are expressed as decimals typically, and those decimals, if they're positive, then there's no sign attached to it typically, and if they are negative or inverse, there is a minus sign in front of the correlation to indicate that it's an inverse relationship. And as I said, the number indicates the strength, and the sign, if it's negative, indicates that it's inverse. If there's no sign, it indicates that it's a positive correlation. Another way to think of Pearson's R is that it's a measure of the relationship between two standardized values, or z-scored values. And we'll get to a formula for that in a moment, but first let's take a look at some scatter plots. Basically, the one in the upper left would be a really unusual thing to find in the wild, but it's good to look at as an example. That would be a perfect positive correlation. Here we have basically no relationship between the variables. Here we have a perfect inverse relationship, whereas as x increases, y goes down linearly. Here we have a fairly strong positive correlation where a linear equation can summarize the relationship between x and y as being fairly positive. So we have a correlation of positive 0.6, and here we have a fairly strong inverse correlation. So I'll post this simulator on our Blackboard page. There's a pretty nifty online tool that allows you to play around with correlations and get an idea conceptually how they work. So I've created in this simulator a sample of 144 cases that have no relationship. So basically these variables are just scattered, more or less randomly around the scatter plot. But let's see what it would look like if we had a correlation of 0.27. You can see kind of the relationship is emerging, 0.37, 0.51, 0.58, and then the closer you get to 1, the more linear and perfect, and the relationship would be able to be very readily summarized by a straight line with a strong slope. And then we can do the same thing going to the left. We can look at what would an inverse correlation look like as it got stronger and stronger. And another thing, there's a few things we can note here. With small samples, let's have a pretty small sample. Let's go with like 30 something. With small samples, so here we have a correlation of negative 0.38, which is kind of a weak inverse correlation. With small samples, there's a couple cases if they're outliers. So let me just move this case way up here and see what it does to the correlation. So it jumped all the way to negative 0.52, or if I moved it down here, it basically wiped out the entire correlation. So with small samples and 1 or 2 outliers in a solution for the correlation, it can cause a lot of trouble. So that's why, generally speaking, we seek to not have very small samples, but sometimes we don't have a choice. But when we have a small sample, it's important to look at the scatter plot to see if there's any really unusual cases that are kind of might be messing with the summarization of your data. How to deal with them is a topic for another lecture, but it's important to investigate a scatter plot prior to testing a correlation. So here's a conceptual formula. I really don't recommend calculating it this way by hand. It's not a lot of fun, but it can help you understand what's going on. We have here a z-score for each variable for x. Here we have a z-score for each variable for y. If we multiply those together and both variables are going in the same direction relative to their mean, so either if both are positive away from their mean or both are negative away from their mean, the resultant product will be positive, right? Because a positive times a positive is a positive, and a negative times a negative is a positive. And that would, on average, imagine this is on average, there is a correction applied here, but that would, on average, if we summed it up and divided it by n minus 1, lead to an overall positive correlation. If the scores for variable x and y are more or less just going randomly up and down away from their mean, and there's no meaningful association or any association between the variables, then we'd end up with a Pearson's R value closer to 0. In the situation where if x went positive away from its mean, then y deviated negative away from its mean on average, then we would get a negative times a positive or a positive times a negative. And if that happened on average, the Pearson's R would then be an inverse or a negative correlation, hence the minus sign that would come before it. I think it's important to briefly note that let's say a more raw measure of association is covariance. So covariance is basically the unstandardized version of Pearson's R, or of correlation, where we're looking at the deviation of each score away from its respective mean, and then essentially taking the average, although there's this correction here, essentially taking the average of the sum of the products of all the deviations away from each score from their mean. So covariance is more of a raw measure of association, kind of like variance is not as interpretable as standard deviation. Covariance is usually not as interpretable as Pearson's are, for the reason that its maximum and minimum scores vary considerably depending upon the standard deviations. So the maximum or minimum covariance that can be achieved is a product of the standard deviation for the x variable and the standard deviation for the y variable. So that's why usually we don't interpret covariance directly. It might be used in equations, and it certainly becomes an important statistic in more advanced statistical applications. But for the most part, when we report relationships between variables, we don't necessarily report covariance. Instead, we might divide it by the product of the two standard deviations, which would yield the Pearson's R value. Here on the left, you have the symbol for the correlation in the population, which is rho. And here on the right, you just have the symbol that you'll usually see, which is the symbol for the correlation in the sample, which is italicized lowercase letter r. And so this formula is one that you might use if you have the covariance and the two standard deviations, but most likely you're going to be using a statistical software program to compute Pearson's R. Otherwise, you'll use a computational formula, which I won't cover here because I don't think it's worth the time right now to be doing that by hand. There is, of course, a null and alternative hypothesis that's being tested, assuming you're using the classical null hypothesis testing, significance testing approach. The null hypothesis will usually, it doesn't have to be written this way, but it will usually say that there's no relationship is expected between variable x and variable y, or in other words, in the population, the correlation is 0. The alternative may be non-directional. It might say that variable x and y are expected to be linearly related, but not state the direction of that relationship, and that will allow the researcher to test the correlation significance in either the positive or negative direction. However, in some cases, it may not make sense to do a non-directional or two-tailed test, and we may instead use a directional test and state that it is expected that the correlation will be positive, or the correlation will be inverse or negative, but not both. So we'll either say positive or negative in terms of the alternative. So if the p-value is low enough, just like with the t-test, and actually it is based on a t-test, if the p-value is low enough, we will reject the null, and what's low enough depends on what the alpha is. We'll reject a null and we'll provide evidence in support of the alternative hypothesis. As I've already mentioned, correlation does not mean causation. There's a lot of fun spurious relationships that you can explore on this website that has a number of kind of humorous spurious correlations. The significance test for Pearson's R is basically, as I said, the null hypothesis is that in the population the correlation equals 0. The alternative hypothesis is that in the population for a non-directional or two-tailed test is that the correlation does not equal 0, and for a one-tailed test it's that the correlation is either greater than or less than 0. The test itself is based on a t-test. It's unusual unless you're doing this by hand to actually conduct the t-test, because most software programs and even most textbooks will have information where you can look up the p-value directly from R, but it is based on a t-test with n-2 degrees of freedom. And it's done pretty much just like the t-test for comparing the means would be done. You determine the alpha, you determine the number of tails and the degrees of freedom, and then you can look up the p-value and decide if the p-value is lower than alpha. Then you will reject the null and say that there's evidence in support of the alternative hypothesis or evidence in support of the correlation that is detected. If the p-value is too high, it indicates that the correlation that you detected is too likely under the null hypothesis. So the lower the p-value means the correlation is less likely under the null hypothesis, and a higher correlation, or a higher p-value rather, means that the correlation is more likely under the null hypothesis. But most software programs will provide you with the Pearson's R value and will provide you with the p-value so that you can directly interpret it. All right, so I'll leave it off there. I hope you enjoyed that information, brief conceptual lecture about Pearson's R as much as I did. And you can watch the subsequent videos for how to compute Pearson's R by hand if you're into that sort of thing, and also the video on how to compute Pearson's R in SPSS. But basically, you're interpreting the R value as the direction and the strength of the relationship between two variables. Closer to 0, weaker correlation. The closer you get to -1 or +1, stronger correlation. And then also it's important to pay attention to the p-values. Lower p-values indicate that the correlation, the evidence might allow you to reject the null hypothesis for the correlation, whereas a higher p-value would indicate that we don't have enough evidence to reject the null hypothesis, so whatever correlation we found in our sample may very well just be a type 1 error. Of course, there's all other sorts of things to take into consideration, in particular the statistical power of the test. So if you have a smaller sample, it may be very hard to detect a correlation that is there if it's a weak one. Or if you have a small sample, sometimes you might just get a chance correlation that popped up in your data, but that is really a type 1 error. All right, thank you for listening, and I hope you enjoyed that as much as I did.